Today we will see general analysis techniques. In any subject, first we should understand what are the techniques that we have to analyze or calculate something in that subject. And in this subject, particularly in networks, as I mentioned in the previous lectures, the first thing is how to analyze that. That we have general analysis techniques. That is why I named this as general analysis is because this is so general, can be applied to any circuit. So any technique for any circuit, that's why this is titled as general analysis technique. So it's going to be more important, and based on these techniques we apply for electrical circuits as well as electronic circuits. That's why one should take a lot of interest to understand these techniques. And these techniques are three types. One is KVL and KCL. KCL means Kirchhoff's current law. KVL means Kirchhoff's voltage law. These are the basic laws. And the second important thing in circuit theory. Why do I say second? Because the first one is Ohm's law. So using the Ohm's law and KVL and KCL, we can analyze. Analysis means calculating output. So when you see this technique, this is used for one or two variables. If the number of variables increase, we have to go to the mesh and nodal. And if it still increase, we should go to cut set and tie set. Likewise, so this is used for number of variables less. And in objective question exam like GATE and PSU, even in IES objective exam, most of the questions will come with one or two variables because the time is very less. That's why this technique itself will cover almost 80% of the problems will be solved by this technique itself. Maybe another 10-15% will be solved by mesh nodal, remaining by tie set and cut set. Therefore, this is very important. These are solved in the form of equations. We apply Kirchhoff's current law equation and voltage law equations. The technique we use is KVL, KCL. What is the advantage here? We determine directly the branch currents. Branch currents we don't calculate indirectly, directly come. Similarly, we calculate branch voltages directly. So this is what it means by one technique called KCL and KVL. Then coming to mesh and nodal. When we talk about mesh and nodal, this is used for two or three variables. When you see two or three variables means it is little bigger than the previous KVL and KCL. And these are solved in the form of equations again. I mean to say we don't take matrices. The need of matrices will come only when the number of equations increase. And we use mesh here, we use nodes there. And initially calculate loop currents. From the loop currents we calculate branch currents. And similarly, if we use nodal analysis, we calculate nodal voltages and then branch voltages. So these are the basic differences or the approach for the problem. Then coming to tie set and cut set, this is actually called graph theory. Some people call it as a topology. This is used for 4 or above variables. If the number of variables are 4 or above, we can't use it in the mesh or nodal. We have to go for this thing. These are solved in the form of matrix, tie set and cut set. Initially calculate loop currents and then branch currents. Initially calculate nodal voltages and then branch voltages. That's why these are for higher level. These are the three techniques we have to understand or to analyze any technique for any circuit, as I said, general analysis technique. Let's now go into details. Today we will be concentrating only on KVL and KCL. And maybe another lecture will go to mesh and nodal, and lastly topology. So this total general analysis techniques we have divided into three lectures. One is KVL and KCL. You see the correct spelling Kirchhoff's voltage law. We call it as abbreviation KVL. What is the law? The law is basically telling the algebraic sum of EMFs and potential drops in a closed loop or closed path is 0. Why do I use this word closed loop or closed path? When there is a capacitor, the capacitor is really open circuit. The current in the capacitor is 0, but in the circuit, current flows when you use capacitor. Therefore, we may not call that as a closed loop, but we'll call it as closed path. This is a special name given when there is elements like capacitor is available in the circuit. That's why the algebraic sum of EMFs and potential drops in a closed loop or a path is 0. KVL is based on law of conservation of energy. This is called law of conservation of energy because it doesn't radiate anything. By mistake, if something is radiated, this cannot take care. We need to go for Maxwell equations. So when you go for Maxwell equations, they can consider anything that is lost or gain. So this is only talking about whatever EMF is given. EMF means electromotive force. Whatever the electromotive force we give, that will be dropped in every other part. Therefore, what is given is dropped, and hence we can call it as law of conservation of energy. Where is it applicable? It is applicable for networks which are not emitting the radiation. For example, if there is a radiation, as I told you just now, you cannot apply KVL and KCL. You have to go for Maxwell equations. Indirectly, EM theory, electromagnetic theory. So electromagnetic theory, that's why we call it as exact analysis, because it considers radiation also. Whereas in circuit theory, we ignore radiation or we assume there's no radiation, that is at low frequencies. Therefore, circuit theory is generally called approximate analysis. EM theory is called exact analysis. Now let's go into an example to illustrate what KVL is. The algebraic sum of EMF and potential drops in a closed loop or a closed path is 0. Whenever you hear the word algebraic means something polarity. When polarity is included, then only this is valid. So we need to know how the polarity is included. To illustrate that, I have taken a small example. You see here, we are going from minus to plus. When you go from minus to plus, this is called plus E. Along the current, we are taking minus. So therefore, plus E minus I into R1 minus I into R2. Please remember once again, when we are going to minus to plus, we say plus. Along the direction of current, we say minus. It is easy to remember, when you say along the current, you are going down. When you are going down to the potential, you can put minus. That's the best way to remember. When we go from minus to plus, you are raising. When you are going to raising, put plus. When you are going to fall, put minus. That's the meaning. That's the way one can easily remember. But I know there is some people are thinking in the opposite direction. They are thinking opposite way. It doesn't matter. If you already learned opposite direction, and if you are now I am introducing another direction, don't worry much, because if you multiply with the negative sign, both are same. Or if you send the whole thing on the other side, both are same. You will not have any problem, but follow whatever that you have the notation. But this is the way we are going for notation. Therefore, this is a way to say E is equal to I1 R1 plus I1 R2 if you take that side. Therefore, total EMF is dropped in resistors. That is the meaning of KVL. Let me take you to KCL. In a circuit, the algebraic sum of currents entering to the node is equal to leaving the node. How many currents entering is equal to leaving? It indirectly says no current is lost, no current is gained. And that is again talking about law of conservation of energy. So it is just like saying some water is entering and the same water is leaving. If some water is lost within, we cannot use this technique. So therefore, another way of telling, in a circuit, the algebraic sum of currents at any node is equal to 0. So there are the two ways. You can say, if you say all currents is 0, or the best way to whatever currents is entering is equal to leaving. But in general, if a node is mentioned, we always assume If we are given freedom for the direction, we assume all currents leaving. That means positive. And KCL is based on law of conservation of charge. This has become a very serious objective question in exams, so many times repeated in IAS exam. Therefore, KVL is based on law of conservation of energy. KCL is based on law of conservation of charge. It is also applicable to the networks which are not emitting radiation. Again, the same condition is valid. We cannot take radiation into consideration. So this is about Kirchhoff's law. Let me illustrate with an example in order to understand the algebraic meaning. Look at this circuit. If you look at this, there are currents entering, there are currents leaving. And when you say I1 entering, I2 entering, so entering is equal to leaving. I3 and I4, I5 are leaving. So 2 currents are entering, 3 currents are leaving. So this is the meaning, entering is equal to leaving. So this is about KCL. Now I am going to problems while using, let us see the problems given in the previous examinations. So let us solve some problems to really, one way to understand Kirchhoff's laws, other way to really cross check whether we really understood or not. Let's see the first question. The first question is the value of R in the circuit shown. That is the circuit shown there, and if the values are, the options are 10 ohms, 20 ohms, 30 ohms and 40 ohms. And when you look at this, we need to check what is the answer. For example, look at this circuit. This is the circuit you have, and here is the circuit as it is mentioned. This value 2 amperes is given. This we need to calculate. Okay. And this is given as 10 ohms. Another given as 10 ohms. And this is given as 100 volts. So this is a problem given to you. And you have so many approaches. In circuit theory, there are several approaches. And in BTech, we may take lot of any approach, no problem. But when you go to competitive exams, particularly objective exam, nobody will see what approach you have taken. In fact, nobody will see the solution. They only want an answer. So therefore, as much as possible, use shortcuts. For example, 90% of problems I would like to solve by KCL, Kirchhoff's current law. Because Kirchhoff's current law is basically will reduce number of equations. For example, if you take loops, you can call this as loop 1 and loop 2. And it will give 2 equations to solve and waste of time. But if you see the nodes, this is one node. Let us say V1. And this is another node that is called ground. By taking this as a ground, people call it as a reference node. Some people call it as ground. Either way, no problem. So once this is treated as a reference node or ground, this is called 0 volts. Now, you can solve this by one single equation. Instead of going for 2 loop equations, you can solve with one nodal equation. Instead of applying KVL twice, you can apply KCL once. When you apply KCL once, as I already said, we always assume all currents leaving by default. If they give their own notation, use your way, their actual notation. But if they leave us freedom, better we say all currents leaving. For example, this current leaving, this current leaving. Don't follow loop equations. You only follow nodes. And these are the 3 currents leaving. Therefore, what should happen? This current plus this current, all these 3 currents should be equal to 0, according to KCL. Now, the best way to solve is this. V1 minus 100 by 10 plus V1 minus 0 by 10 plus 2 is equal to 0. V1 minus 100 by 10, V1 minus 0 by 10, V1, this is already a current. You can solve it. If you take LCM, you can say V1 minus 100 plus V1, this becomes 20. So therefore, this is minus 100 plus 20 is becoming 80. So therefore, 2V1 is 80, and hence V1 is 80 by 2 is 40 volts. And this we understood now as 40. If that is 40, what is the value of resistor here? The value of resistor here is voltage by current. Therefore, 40 by 2 is 20. If you come to options, if you see their options, our option you can easily see B is the option that you have. You can also see the solution here. So whatever that we have worked out, you can also see here. So this is to make you to understand, but that's already there. Answer is, the option is B. So this is the first problem I have taken to make things very simple. And this is the analysis that we do. And let's go to second problem. And when we go to second problem, read the problem first. In the network shown in figure, the effective resistance faced by the voltage source, that is, options are 4, 3, 2, 0. There are 4 options. And when you look at this circuit, solution is also given here. Look at the solution there. The best way to see is, the circuit is already here. Suppose this is current, as he said, this is I by 4. And please understand, this is a dependent source. I by 4. Therefore, I by 4 is leaving, 4 ohms is here. And the voltage between that 4 ohms is nothing but V. Therefore, I entering is equal to I by 4 plus V by 4. And if you take this side, I minus I by 4 is equal to V by 4. Therefore, total is 3I by 4 is V by 4. 4 and 4 if you cancel, V is equal to 3I. That is Ohm's law. If you identify from there, the effective resistance is 3. That is how one can really solve this problem. That is basically dependent source is involved here, and also another Ohm's law is involved here. Let's see. The answer is B. B means 3. In the circuit shown, the power supplied by the voltage source is A 0 watts, 5 watts, or 10 watts, or 100 watts. These are the 4 options that we have. And when you look at the circuit, this is the voltage source given. From there we calculate different currents going through different paths. And if you observe here, for example, the circuit is this. You can put the reverse order, or you can say this is one current source given to us, and then another current source given to us. Then you have a resistor, thing is going up. Or we will then if you connect that one here, there is another resistor also there. This is one current also here, 1 ampere, 2 amperes. Then a source is given here. The question is, from this voltage 10 watts, 10 volts, how much power is supplied? So to calculate how much power is supplied, here also there is a resistor, 1 ohm. This is also 1 ohm. This is 1 ohm, 1 ohm. All are 1 ohm resistors. But one thing you can appreciate, 2 ohms coming here, 1 ohm coming from here. Therefore, here totally you can say this and this is coming, and you can say 3 amperes here. 3 amperes, because this is entering, this is entering, this is leaving. And if I call this as I, let us see the solution here. In the same circuit diagram you have, if I call this as 3 and if I call this as I, this is I plus 3 amperes. I is coming from here, 3 amperes is going here. Then what is the total drop we have? You can apply KVL outside. You know why? When there is a current source, you cannot apply KVL. You cannot apply KVL here. The best option is go here, go here, go here. This is a loop. Therefore, let me apply 10 volts minus 1 plus 1 is 2 into 3 plus I. Then from here, and if you really calculate, what are the different options that you have? This is one equation, you can come by that. Suppose if you say this is equal to 0, okay, there is another current here. So what is the current in this path? You can apply. So calculate the current here, and suppose this 1 is here, I plus 3 is here. What should be the current here? I plus 3 is entering here, 1 is going here. Therefore, it should be 3 plus I plus 1. That means 4 plus I. That's why when the current is coming this way, you can call that. And actually, there is a 2 ohms here. If you calculate and say minus, so 3 plus I into 2 minus 2 plus I into 2 is equal to 0. 2 plus I into 2. Because this is the current going, When this current is I, this is also I. What's the current in this path? 2 plus I. So please understand, this is I, this is 3, therefore I plus 3. And here same current I has to come, then 2 is going here, this should supply. Therefore 10 minus 1 plus 1 into I plus 3. Then instead of saying 4 plus, you can say 2 plus I into 2. Therefore this becomes 10 minus 2, 6 minus 2 I. This is again minus 4 minus 2I, like this. So if you calculate from here, how much is this? 10 minus, this is 10 minus 10 minus 2I minus 2I. That means 10 minus 10 is 0, therefore I is equal to 0. If I is equal to 0, what is the total power supplied by this? Power is generally called V into I. Therefore 10 into 0 is 0. Therefore that is our option. The option is power A. What is option A? If you go back and see the question, 0. So the total power that is supplied by the source is 0 because current is 0 here. This is how you can solve.